Hello, good evening all.
Good evening, ma'am.
Yeah, so how many of you have studied week 9?
I think how many of you understood probably a better question. Sorry.
Okay. So I was thinking like next week is your quiz, right?
Yeah.
So I was hoping most of you would not have studied week 9.
They're hoping to get an extension after the exam to submit the essay.
I'm not week 9. I don't think so. No, it is next week only.
Yeah, because
It will be not extended, ma'am. That means.
Yeah, it will not be extended. For sure.
it is chipping out some time, which otherwise you would have spent it for the exam preparation.
Yeah, so yeah, let's study week 9 properly this week, and next week we'll focus properly on week like the previous weeks, right?
So, ma'am, one more little question from the quiz 2. So it is only from the week 5 to 8, or it is week 1 to 8?
Expect some portion from week 1 to 4.
Okay.
Yeah.
It is 10, 20%, something like that from week 1 to 4.
That I cannot say, but not much, I would say. Even if it is there, I hope you all will be able to do it.
Okay. And ma'am, when will the mock of the
Mock
quiz?
is scheduled on Monday, so you will get like you will get your mock on Monday.
Okay. Tomorrow.
Yeah.
Sorry.
Monday.
Monday. Yeah, sorry.
Monday.
Yeah. Okay.
How many marks, madam?
You will have one mock.
Is it an assignment type of thing, or it's a timed one?
That you will get to know.
Oh, okay. But
Yeah.
that is graded considered in the scoring?
Yeah, so like you get some marks for attempting mock and practice assignment, right?
Yeah.
Yeah, so you should do it. Like the mock is important.
Okay.
Ma'am,
Not just because you get marks out of it, but also it gives you a feel like what kind of questions right you get. Yeah.
And ma'am, how many questions approximately in the quiz second? It is 15 or 20?
You will get to know from the mock paper.
Okay. It is similar. Okay. Thanks.
It will be kind of similar. Yeah.
Okay. Thanks.
ma'am, can I ask a question on extra activity?
Extra activity, no, let's not put it here. So
Okay.
yeah.
Fine.
When is mock test scheduled, ma'am?
It is scheduled on Monday.
This Monday only?
This Monday, yeah. Okay, so let's start the session now. Okay, so before we start, have you gone through the lectures? How many of you have gone through the lectures? Can you raise your hand?
Some of
We
them
have
not
started,
plugged in.
but not completed.
Okay. Nikhil has gone, Ganga Prasad, Rajiv, Ravi, Dripto, Smita, Harishankar, Sanchita. Okay. Okay. Only some 9 people. Okay. Okay, let's start. Okay, so before we start that properly, like I will just give you an idea like what exactly we are doing in week 9. Okay. So week 9 is about parameter estimation. Okay, mute yourself. Yes. Yeah. So in parameter estimation, so what we are doing is, like you have seen in week 7 that we were taking IID samples, right? So we were taking IID samples, and from there we were trying to um, okay, basically we studied how do we collect samples and everything in week 7. But now here what we are trying to say is, like, let's say you have a population, okay? Let's denote this population by P, and let's say this population has some underlying distribution. Let's say it has the distribution, let's denote the population by X, and it has the distribution fx of X, okay? This fx of X can be anything. If X is a discrete distribution, it is going to be PMF, or if it is a continuous distribution, we'll say it is a PDF. And this distribution has this random variable basically has a lot of different parameters associated with it. Like, let's say if X was Bernoulli, right? If X was Bernoulli, so what is the parameter that we have for Bernoulli distribution? P, right? It has a parameter P. Now let's say if X is normal distribution. So what all parameters do we have for normal distribution?
Mu and sigma square.
Mu and sigma square. Now let's say X is a gamma random variable. So what all distributions do we have?
Alpha and beta.
Alpha and beta, right? If we have exponential, we say it has a parameter lambda. Similarly, so we see that each of these random variables distribution have some parameters associated with it. So let's say we have a population, and we don't have much, we have the data, and we don't have much idea about like what all the parameters are there. We have, let's say, some idea that like looking at the situation, whatever data we have collected, let's say according to that we are saying that this model's a Bernoulli, this is a Bernoulli setup, or sometimes we say it is a Poisson setup, binomial setup. So we just know only that, but all these random variable have some parameter associated with it, and these parameters are unknown, right? So the basic idea is, like, what we're trying to do here is, how do you estimate those parameters? Okay, so these parameters, like this P here, or mu, sigma square, so all these are called parameters. And what all these parameters are? These parameters are unknown. Okay, we don't know what these parameters are. Looking at the data, we don't know what these parameters are. We just say, we just know that these parameters are unknown to us, and it is a fixed constant. It is going to be some fixed constant, right? Given a data, whatever distribution your data is following, it will have some parameter. Is that fine? Now, so now how do you find those parameters, right? How do you estimate? We cannot exactly find our parameters, but at least we can estimate these parameters. So this is what we are going to do in this whole week. We are just trying to estimate our parameters. Okay, so the basic setup of the basic setup of parameter estimation is, let's say you have n IID samples, okay, x1, x2, xn. So if I'm saying x1 to xn is an IID sample, so like these all are random variables, right? This we had discussed, these capital X1, capital X2 to capital Xn, these all are random variables, and realization of these random variable will give you one sample. So we are just saying, let's say this x1, x2, xn is one like NID samples, and they are coming from the distribution x. And let's say the distribution x follows like x has some distribution, okay, and that distribution has those parameters, let's say theta 1, theta 2 up to theta 3. It can have many parameters, it can have just one parameter, it can have two parameters, it can have three parameters, and so on. So let's say your random variable x has some distribution, and that distribution has those parameters theta 1, theta 2, theta 3, and so on. So in the like general setup, what we are doing is we are saying these theta i's are our parameters, okay, and these parameters are unknown but fixed constant. These parameters are unknown, but it is a fixed constant. Now, to find these parameters, like we have a function defined that we called as an estimator. Okay, so for this parameter theta, let's say the parameter is theta, we will have a function that we call as estimator of theta, and we denote this estimator by theta hat. And what exactly is theta hat? Theta hat is an estimator. Theta hat is going to estimate your parameter theta. So this is an estimator, and this is nothing but a function of, so you have a sample, given one sample, you give one sample, let's say x1, small x1, small x2 to small xn, given one sample, this theta hat is going to give you a fixed value r, some real numbers it will give. Okay, so we define our estimator theta hat to be a function of the random the function of these random samples, and it is going from basically we can write this as theta hat going from this sample x1 to xn to r. Okay, so this is one way to denote your estimator. So you get, so you have a data, you have the data with you, and you take different samples and you will get different r. Okay, the way your estimator is defined, you will get different value for the estimator. So one thing to note down here is that your estimate, the estimator, this theta hat is an estimator, and this is a random variable, okay, because it is a function of the random sample, and the sample is going to change, like the sample will keep changing, right? So since the sample is changing, you will get different values for the samples, the way estimator is defined. So basically estimator is a random variable, but your parameter theta is a fixed constant. So you should always keep this in mind. Okay, so any doubt till here?
If theta hat is an estimator and estimates theta, then why is theta a fixed constant?
Okay, because theta is not your sample parameter, right? This is fixed because it is from distribution. Like given a population x, given a population x, you have some distribution. Let's say x has Bernoulli distribution, okay, and it has the parameter p. So if you have some data, it is going to follow some distribution, and the parameter is going to be constant, right? So here I will not say that p is unknown. This p is okay, like this p is unknown to us, but it is going to be some fixed value.
Okay,
It is
in a
going to be some
distribution,
fixed
yes,
value,
okay.
right?
Yes,
So
yes.
this theta is, so in place of P, what I'm doing is I'm just writing theta. Okay.
Okay.
Theta is an unknown parameter. Sorry, theta is unknown, but it is of some fixed constant that we know. Now what we are doing is, now from that population we are taking samples from there. So you take one sample. So whatever way the estimator, so whatever estimator you have, okay, whatever estimator you have, given different samples, you will get different values, right? Like,
Yeah,
let's say,
if I take a lot from the population, then I will get some kind of a, yeah, okay.
Like for example, let's say I have x1 xn, let's say this is one sample, this is NID samples from, let's say, Bernoulli P distribution. Okay, so we know that the distribution, the population distribution is Bernoulli, and but its parameter P is unknown, but some fixed P, right? Now I have designed few estimator for to estimate these parameters. Okay, I have designed few estimators to estimate this parameter. Let's say my first estimator P1, what I'm saying is P1 hat, this P1 hat is 1 by 2. So what do we mean by P1 hat equal 1 by 2? It means you take any sample, from the population, your estimator will always give you the value 1 by 2. Right? Now I can define some another.
So basically it's a constant function.
This one is a constant function.
Okay.
Like you take any sample, sorry, I think this doesn't explain what we had asked. Let's stick to that, why theta hat is a random variable. Okay, so theta hat is a function of it is a function of samples, right? It's a function of n random samples.
And
Now,
random variables, right?
sorry, n random variables, right? So you take one sample, and for that particular sample, your theta hat will give you a particular value. So for some other sample, your theta hat will give the other value, right?
Yes.
ma'am.
So
Yes.
depending on what samples you are taking, your theta hat will keep on changing. The value that theta hat, the estimator will fix, but whatever values this estimator will give will keep changing depending on what sample do you have.
Yes.
So
That's
this
why-
is why
Yes.
we are saying it is a random variable.
Yes.
Okay.
Okay.
Because each xi is okay, is a IID, as you said, that itself is a random variable. Okay. Okay.
Okay. So this you have to keep in mind that theta hat is
Hello.
I
We
think-
can't hear you, ma'am.
Yeah, we can't hear you.
Hello.
Did she lose her connection?
okay. Yeah, I had lost my connection. I will share it again. Yeah, it is visible, right?
Yes, ma'am.
Yeah. So, okay, till here it is fine.
Yes, theta cap is a random variable. This is clear.
Okay, so there were few examples that was done in the lecture. Just give me a minute. Okay, so what we saw is that theta hat is an estimator of the parameter theta where theta hat is a random variable and theta is an unknown constant. Okay. So let's look at few like example. Now you have taken NIID samples from a Bernoulli P distribution. So we do not know what this parameter P is. We just know we have a distribution for the population and it follows the Bernoulli distribution. But what the P is, we don't know. So we want to estimate this parameter P. So for that, we have designed few estimators of P. So there are few estimators of P that we have designed. So let's say the first estimator that we have designed, let's denote this by P1 hat, and this is 1 by 2. Okay, so what does it mean is you take any sample. So P1 hat we know is a function of n random variable. So you take any sample, your this the value that P hat will give is going to be fixed. So this is what we mean by P1 hat equal 1 by 2. So we can say it is a constant parameter. Constant estimator. Then second is, let's define it as x1 by 2. X1 plus x2 by 2. So this is some other estimator for your parameter P. So depending on different samples, you get your P2 hat will give different values. So this is one way we have defined an estimator for the parameter P. Then we have the third parameter, that is P3 hat, and it takes into consideration all the samples that we have. Okay, x1 plus x2 plus xn by n. So given different samples, so let's say I have taken, first talk about estimator 1. So for estimator 1, that is P1 hat equal 1 by 2. We know that the samples are coming from Bernoulli P distribution. Okay, so let's say the first sample that we observed is some 1 0 0 1 1. Let's take it is a sample of size 5. Now from here we'll say that this is going to be 3 by 5, that is 0.6. Sorry, this is one sample that you have observed, and according to this estimator P1 hat equal 1 by 2. So any sample you take, your estimator should give you the value 1 by 2. So even if you take a sample that is 0 0, even if you take another sample, let's say 0 0 0 1 1, still your estimator will give you the value 1 by 2. So even if everything is you get is 0, still it will give you the value 1 by 2. So it doesn't matter what your sample is, your estimator is always going to estimate your parameter as P equals 0.5. So this is kind of not right, because what we want is we want our estimator to be close to the parameter. Okay, we want this like the error that should happen between your estimator and the parameter should be as less as possible. So this is kind of a very biased estimator, we can say. Like any sample you are getting, any sample you give, your estimator is always going to give you 1/2. So this is not a kind of good estimator. Similarly, for the same samples, if you take the second estimator into consideration, so your P2 hat will give you for the first sample 1/2. For the second sample, it will give 0, and for the third sample, it is going to give the value 0. So so what is happening here is, just on the basis of the first two samples that you have, the first two numbers that you have observed, what you have observed, just on the basis of that, it is going to estimate your parameter. So that is also kind of not good, because we are just here talking about two samples. We are forgetting about the another n-2 samples that we have taken into consideration. So this is also not a good estimator. We'll not say this is a good estimator. But if you look at the third estimator that we have designed, that is nothing but a sample mean. So x1 plus x2 plus xn by n, right? So this is your estimator. And if you find like P3 hat, so actually this is not a very good sample that I've taken here. So just make some changes. Make it one here, get one here. Okay. So if you do P3 hat, right? So for the first sample, you're going to get 3/5. For the second sample, again, you're going to get 3/5. For the third sample, you're going to get some 2/5. So there is not much fluctuation in the values that this estimator, this sample mean is giving you. So there is not much variation, right? So basically the error is less, kind of like between between all these three values, like for three different samples that your estimator is giving, the variation in the values are less. But if you look at the first two cases, in the first case, it is always giving you 1/2. In the second case, the variation is too much, it is 0, 0, then 1/2. So that is also one thing that we keep in mind when designing the estimator, is like your variation in the values should be less. Okay, so we say this third estimator that we have, it is called a good estimator. So why it is a good estimator, we'll see it later. So okay, any doubt here? Okay, let's
No,
move.
ma'am. No.
So far, it's okay, ma'am.
Fine, ma'am.
Okay. Okay, so what I had said before is, like, we also want our estimator, like the error between the estimator and your parameter should be as less as possible. So the estimator is theta hat and the parameter is theta. So what we want is, whatever estimator we have designed, we want this estimator to be as close as possible to our parameter theta. So let's say if the parameter theta is here, so you want your estimated theta hat to be in some close neighborhood of theta. So you want your theta hat to be in some close neighborhood of theta. You don't want this theta hat to be so far from this parameter. So there is a term that we define. This is called error, and this is defined as theta hat mod of theta hat minus theta. So what we want is, we want this error. So basically we want this error to be as less as possible, right? So this should tend to 0. So what we want is probability that this error is greater than some, like the distance between the parameter and the estimator should be so less, and this probability should tend to 0. Right? So what does it mean? It means that if your parameter theta is here, then this is going to be theta plus delta, and this is going to be theta minus delta. So the probability, and this, what is this delta? Delta is very small, some very small value, very less than equal to 0. Okay. So this delta is a very small value, and you want this probability that your theta hat lies in this interval should go to 0. So once this error goes to 10 to 0, it means they are very close. Like, it means we have found a good estimator, we can say, right? So generally, what we want is, like, what we would want is that whatever estimator do you have, whatever estimator you have, you would want that estimator to be less than, like, your error should be less than tenth of that parameter. We just assume it. Okay. So because we would want that, we want the difference between the estimator value and the parameter to be very less. So one ideal thing that we can do is, we can take this, we can put delta to be p by 10 or theta by 10. Theta by 10. So whatever parameter value do you have, you would want your delta to be so small, some 1 by 10th of the parameter value. Now, whatever example of the estimator we took previously, so the first one was P1 hat equal 1 by 2. Right? So if we have to write the error, what we will write? We will write this as 1 by 2 minus P. Right? So you want this probability that this is greater than P by some P by 10, and it should tend to 0. Right? So okay, so how many of you have watched this lecture where the graph has been plotted, and on the basis of that we were trying to find the p value, like, or what value of p?
Ma'am, I think this is the content of lecture number 3. So
Yeah.
still we have not reached up to graph part. Graph will come in next lecture. So before that, I think Chebyshev's inequality will come into play. So I have a doubt over there.
Okay, no.
Just to ask you, madam, why is it that we're choosing greater than p by 10?
That's a thumb rule.
Like, it just not, it's not, we have just assumed, we have just taken a value of delta here,
That's what I'm saying.
because we would want this delta to be very small, right?
Correct.
So
Correct.
that small, we have taken it as 1 by 10th of the parameter.
1/10. Okay, you
So since the parameter
theta by
was
10,
theta,
hence it is p by 10 over here. Okay.
yeah.
Okay. Okay.
So this is just one value of delta that we have taken. Okay. So, okay. If you draw the graph of this, okay. So how does 1 by 2 minus v will look like?
Straight line.
I will just draw it here. You can check it later. Okay.
Like a U shape, ma'am.
So,
Yeah, this shape. Yeah.
so this is 1 by 2. This is your p, okay. And this is giving you the error. This line over here is giving you the error. This and this. Okay. So this is error, and this is 1 by 2. This point is 1 by 2, right? And what we want is this error should be greater than p by 10. So p by 10 will be something like this. Okay, so this is your p by 10 and this is your error, right? So we want this probability that your error is greater than this p by 10, right? So this error is greater than p by 10 for p is 0 to this value. So whatever this intersection point is, you can find this intersection point. So it will be okay, so this line is p minus 1 by 2, right? And this line is 3 by 10. You equate this and you are getting this value to be okay, it is 5 by 4. You can check these values, okay? And this is 5 by 9. So what we are saying is, like for p lying between 5 by 0 to 5 by 4, right? For p less than 0, for p less than 5 by 4, your this probability is going to be 1. And like for p less than 5 by 4 and for p greater than 5 by 9. P less than 5 by 4 and p greater than 5 by 9, your probability that
Shouldn't
error
it
is
be
greater
5
than,
by 5 by 11? I think. I think that was in the
is it
lecture.
coming as 5 by 11? I'm not sure.
I think that's what was in the lecture. Because 5 by 4 is actually greater than 1, right?
Right. It is not possible. It should be 11, right? Okay. So for p less than 5 by 11 and for p greater than 5 by 9, probability that your error is going to be greater than p by 10 is 1.
Madam, one question here. Not that I'm questioning this inequalities or what the probability is, but it's either a 0 or a 1 directly, isn't it? If it is in the bounds, it is going to be less than p by 10, which means it's going to probability that it exceeds is 0. If it is outside the bounds, it is going to be 1. So what is the advantage? That's my question.
Can you repeat?
When we go for a bound which is less than rather values less than 5 by 11, or for values greater than 5 by 8, the probability, half minus p mod is anyway going to exceed p by 10, correct? So
no, it is not exceeding p by 10 for the values for p that is lying between 5 by 11 to 5 by 9.
Correct. In between it will not exceed. Outside them it is going to exceed. So it's more of a 0 or a 1.
It's
if it is
more of
within
a 0.
A probability that it will not exceed is 0 within the bounds 5 by 11 to 5 by 9, and it is going to exceed is beyond the bounds, more than 5 by 9 and less than 5 by 11. So why do I need to associate probability with this is what I was trying to understand.
Okay, so
it's a value of a function is what I'm saying. Like within this bounds, this particular function 1 minus p mod of 1 by 2 minus p is going to be less than p by 10. Outside the bounds, it's going to be greater than p by 10.
We want this probability to be almost going to 0. It means the probability that it is outside this interval, right? Probability that it is outside this interval. We want this to be almost 0.
But outside the interval is going to give me more than p by 10. That means it's a probability that the error is more than that value is what it is. So I will always get a 1 beyond the bounds.
You will always get a 1 beyond the
bounds.
So
you're talking about this example, right?
Yes, whatever is drawn over here.
Okay.
Am I mistaken in understanding? That's what I'm trying to.
No, that is fine. So why Okay, so why we are saying it is 1 is because this interval between 5/11 to 5/9, it is very small, right?
Correct. That is agreed. That is agreed.
Yeah.
But my question is, why am I associating probability with it? Because it is a definite value. It's either a 0 or a 1. Within the bounds, it is 0.
No, it is between 0 to 1, right?
But it will not be greater than p by 10 within the bounds, isn't it? It is going to be less than p by 10.
Within the bound, it is not going to be, yeah.
So that's a probability of that happening is 0. Outside the bounds, it is going to happen. So probability is 1.
Yes, then probability is 1 there.
So if it is a 0 or a 1, why am I not going for a function? Why am I going to go for a probability wherein a range of values are between 0 and 1? Like I can have a 0.1 or a 0.2 or anything, isn't it? So that's the reason why I'm a little, let me say, trying to understand why we are applying probability here.
Actually, we are checking for probability between 0 to p, which values are taking 1 or which values are taking 0 for that specific estimator.
Correct. I understand. I understand that part. See, 1 minus 2 by p, mod of 1 minus 2 by p being greater than p by 10 is what we are trying to figure if it is going to be greater than p by 10 or less than p by 10. So
For
it's
what
going to
values
be
of p?
for what? Any value of p. Take any value of p.
No. For p values between 5/11 and 5/9, it's going to be 0 or 1. So that values we are going to determine for various estimators.
Come again, please.
For various estimators, we are going to determine for what values of p the estimator is going to lie below p by 10 or above p by 10.
Like
Various
basically,
Why
estimators.
are, why are
like
we
we have
inter-
3
why are
estimators
we
here, right? We had defined 3 estimators. So we are now trying to check what estimators will give you a less error, basically. So, right. So for first estimator, we saw that for like p less than 5/11 or p greater than 5/9, we are getting the probability equal to 1. Like error is lying between error is greater than p by 10. That probability is 1. Similarly, we are doing for the second second estimator, and from there we are checking for what values of p you are going to get um, for what range of values of p are going to get this error to be 1.
We are trying to minimize the error all along, isn't it?
Yes.
Below p by 10.
Yes, it should be below p by 10. Ma'am, can we say like this, that in this case, most of the time, error is greater than p by 10?
Yes, that's correct.
Correct.
Okay.
I think ma'am has lost connection again.
No. I have not
Okay.
lost connection.
Okay.
Yeah. So so similarly for the estimated 2, that was x1 plus x2 by 2. So similarly for this estimator, you will have to check for what values of P your error term, that is x1 plus x2 by 2 minus P, for what value of P it is going to be 1. So can you do this calculation?
What was P2? You had taken one example. No?
Where to graph it? Na?
Okay, wait. Okay, since you have just two random variables, right? So either it is going to take the value 0 or it is going to take the value 1. So let's say both are taking value 0, then 0, 1, 1, 0, 1, 1, right? So on the basis of that, your error is going to be what? Your error is going to be x1 plus x2, that is 0 plus 0 by 2 minus of P. So this is P, then 0 plus 1, this is 1 by 2 minus P. This is again 1 by 2 minus P, and this is 1 minus P. Now, what is the probability that x1 equal 0, x2 equals 0?
That will be varying, na, ma'am.
Okay,
That
I'm
is
asking.
Ma'am, why not
I'm
x
asking.
That is 1/4, no, ma'am. Probability of x by
1/4
x.
of what?
1 by 2, 1 by 2.
1 by 2 into 1 by 2.
Uniform.
But,
Then only it will be
but
one.
do you know what P is?
1 minus
Don't
P the
know,
whole
ma'am.
square.
Sorry.
Okay.
To graph it,
1 minus P the whole square.
Can you repeat? Your voice is breaking.
1 minus P the whole square.
Yes, it is 1 minus P whole square. So why is it 1 minus P whole square?
Because 0 takes the
Pro-
value 1 minus, takes the random variable x takes the value 0 with probability 1 minus P, and twice that,
Yes.
not twice.
Yeah, right. Yeah, so a probability that your random variable x1 is taking the value 0, it is 1 minus P, and probability that your random variable x2 is going to take the value 0 is again 1 by P, 1 minus P. So we're just squaring it up. So similarly, for probability that x1 equals 0 and x2 equal 1, it is just P times 1 minus P. It is again P times 1 minus P, and this is P square. So these are the probabilities, probability of error, right? Now you will have to plot this graph. This graph is
Ma'am, it's not clear about the probabilities. How did you get that one?
okay. So x1 is what? X1 equals 0 means your first random variable is taking the value 0. So
Yeah.
0 represent what? 0 represent
Failure.
failure, right? Failure. And we know that x1 is coming from a Bernoulli P distribution.
Right.
X1 is coming from Bernoulli P
Probability of
distribution, right?
success is P. So that's the reason. 1
Yeah,
minus
probability
P.
of success equal P. So probability of failure equal 1 minus
1 minus P.
P.
Oh,
And
okay.
since
So
they are IIT,
x1 and
we
x2,
just
1
have
minus
to-
P, so 1 minus P goes there.
Yeah.
P into 1 minus P, P into 1 minus P. P square. Okay.
Okay, so here you have 4 terms of error, and you will have to plot all of this. And from there you will find for what values of P your probability is going to be 1. Can you try to plot the graph of this?
Ma'am, I'm sorry I did not get the probability calculation. If it's possible, please repeat one more time.
Okay, I had just told. That these xi's, right? These xi's are coming from Bernoulli P distribution, where P is unknown. Now, this x1, x2 is IIDX, right? So what is the probability that x1 equals 0? What is the probability that x1 equals 0?
1 minus p. 1 minus p.
1 minus p. Similarly, probability that x2 equals 0 is 1 minus p. So it is going to be 1 minus p whole square.
Whole square.
It's just the product of the marginals actually. So
Yeah.
Oh, so these are joint probabilities. I thought these were like the probability which you written above the equation.
No, no, no.
how do we actually plot this? I'm not really sure.
How do we plot this? Okay.
In the lectures, professor didn't elaborate, but he just gave us some values, but I didn't think he elaborated on how
Yes.
he got that.
Okay, so
just on a graph.
right, let's plot it here. I already have the graph. Okay. So this is your P. So the first one is minus P, right? Okay, so 1 minus 2 by P.
We will have to take a value of p, then only we will be able to plot it.
Sorry?
I think we will have to take a value of p.
It will look something like, I will just draw it. You can check it later. Okay. So the first one is going to be you have 1 by 2 minus P mod. That was this 1 by 2. Then you have 1 minus P mod. So this is going to be 1. So basically this blue line over here. So this graph is, this blue line is, okay, what happened?
1 minus p.
Yeah. This is 1 mod of 1 minus P. Okay. Now this plot in black line, this is mod of 1 by 2 minus of P. Okay. And then you need mod of P, right?
0 minus p.
Then you need mod of P. So, you know, this is a mod of P. Okay, I missed one more line here. So this is your mod P, right? So this is a mod P. This is a do this. So mod of error is going to be mod of minus P, or you can write it as mod of P, then 1 by 2 minus P and mod of 1 minus P. So these are the graphs that we have drawn. And if you take the intersection, so with intersection with P by 10, right? So if this is your p by 10, this comes out to be 5 by 11. Then this comes out to be 5 by 9. This comes out to be 10 by 11. And this comes out to be 10 by 9. Okay. Just check these values. And we want our error to be greater than p by 10. Right. So let me take some color. So you see that for values for p less than 5 by 11 and for p lying between 5 by 9, no. So for p less than 5 by 11, you can see that this error term is greater than p by 10. This is some complicated graph. Okay, so for what values of p we are getting this probability to be 0?
One by 2, 1.
Sorry?
1 by 2 and 1. P is equal to
1 by
half
t to
and
1.
P is equal
No,
to
so
1. We get
for p less than 5 by 11, p less than, I don't know if this color is visible. P less than 5 by 11, you can see that this error is greater than p by 10. Right? Then for p lying between 5 by 9 to 10 by 11, p lying between 10 by 5 by 9 to 10 by 11, for this interval also you have error greater than p by 10, right? For p less than 5 by 11, for p lying between 5 by 9 to 10 by 11. Then for p lying between 10 by 11 to 1, you see that the error term is less than p by 10. So for these values of p, your probability is coming to be 1. Either you take the value of p to be less than 5 by 11, or you take the value of p to be in between 5 by 9 to 10 by 11. This probability is coming to be 1.
Y is an error value, is it?
Sorry? What is
The
an error
axis,
value?
y-axis is the error value. What is the
There
y-axis
we
here?
are, this is error. Y is error. Or I can
And
say
what is our
some
objective is
function
to
of
reduce
p.
our error, is
Some
it?
function of p.
So our objective is to reduce the error, is it?
Yes.
Yes. So we are focused at p by 10. I mean, we are focusing on the values less than p by 10, right?
We are taking the delta to be p by 10. In p by 10 neighborhood,
Delta between?
sorry, delta is
No, delta.
p by 10. In the delta neighborhood of p, so p plus p by 10, p minus p by 10. So the probability that your estimator p hat lies between this region should be less, we are expecting.
Less than p by 10, right, ma'am?
Basically this interval.
Yes, error is less than p by 10 in these intervals.
Yeah, but how are we cross mapping this line graph to the other graph? You're telling that P should be
What is the other graph?
line between P minus. Yeah, the line graph result is supposed to be reflected in the top graph, no? Are we really doing that? I'm not able to connect these two. Line graph is clear, okay? But here,
Yeah.
I'm just at a loss.
From here, what you can just take is like, if I just hit this part. So from this graph that we have plotted here, from here, what you just take is like, for if P is less than 5 by 11, if P is less than 5 by 11, probability that this estimator is like this error term is greater than P by 10 is 1, right? And for P, if it lies between 5 by 9 to 10 by 11, right? Then also probability that your error term is greater than P by 10 is 1.
It's 1,
for
is
these
it?
intervals of P. Yeah, is 1.
Between 5 by 9 and 10 by 11.
You see the graph,
The P value is
you see the
1.
graph, error is above p by 10 line. Error is above p by 10 line. That yellow
Yeah,
line.
but there's a small portion. There's a small portion below the P by 10.
That is the region where my error is less than p by 10. My expected, no, I'm to design. I'm designing an estimator where my error should be less than p by 10. Means it should be 1/10 of my parameter. Error should be 1/10 of parameter. So that is the region only where this condition is getting satisfied. As far as this estimator is concerned, P2 estimator is concerned, right, ma'am?
What does
did you
that
say?
mean? Like the estimator works between the range 5 by 11 to 5 by 9 and then from 10 by 11 to 1.
Yes, and then again from 1 to 10.
I didn't get this part. Like, what does it mean? The estimator works.
It will become more clear when she brings P3 estimator into picture. Where I think we will come to know that P3 is an estimator where most of the time my error is less than P by 10. Then only we will come to know that. Here we are trying to understand that which estimator is more promising.
Yeah, as Ganga Prasad has said, and also Anirban, you had also pointed out that our error should be less than P by 10, right?
Correct. If you just try to recall estimator number 1, in that case, there was only very small area when my error was less than P by 10. Here, at least I am getting 2 intervals, like from P by 11, 5 by 11 to 5 by 9. My error is less than P by 10, and again from 10 by 11 to 10 by 9, my error is less than P by 10, right? So at least this is slightly better than estimator number 1, and once we go to estimator number 3, this area will further increase.
Hold on, Ganga Prasad, hold on. P x-axis P is probability, right? Can't be more than 1, right?
You can just like stick to 1. It's okay.
Yeah, we can do that.
Yes, Anirban, go on. Anirban, go on.
Sorry?
No, Anirban was saying something. Yes, Anirban.
No, I said that I think we should stick till 1 and should not go beyond 1. That was what I was trying to say. Because P is probability, right?
It's okay. You can just assume the graph till here. It's fine.
Okay, even if we stick to that part also, in case of P2, in case of this estimator, my area where my error is less than P by 10 is slightly more than estimator number 1. It means estimator number 2 is slightly better than estimator number 1. Once we go to estimator number 3, then it will further, situation will further improve. This is my understanding. I may be wrong.
No, that
This
is
is what I
right.
understood
So,
too. Yeah.
yeah.
Ma'am, may I make a humble request? Can you just draw what was the graph or whatever it is for estimator 1
The
besides
graph for the
this?
first, okay, we'll
Besides this,
just
ma'am,
plot it
just to
here.
put things in perspective, please.
It's
So,
isn't
okay,
that already in the picture?
the first one is not there.
Yeah, it's
What I can do is I will plot side by side here only.
it's
I'll
1
just
by
move
2
some
minus p,
part.
right?
It
It's
is
there,
already
madam.
there. Right.
It's already there.
It is already there. Right. So it is.
Which one is it, ma'am?
This is
Ma'am,
one. This
You
1
see
by 2
the 1
minus
by
p.
2 part, right?
1 by 2 minus p.
ma'am, you asked a question that at what value of P the error is becoming 0. That's the question you made it.
At what value of p the error is? I mean, you want
The
your error to
error
be
value is
less.
becoming 0.
You want just error to be less. I mean,
How do we quantify less? You had given an equation mod 1 minus P. Okay, the last equation of the line is mod 1 minus P. And that's a straight line. Okay, the one line starting from 1 is the
1,
straight
2.
line
Yeah.
for the mod 1 minus P. Yeah, now the error value to be 0 for that, P should be 1, is it?
Actually, it was mod 1 by 2 minus p, right?
Huh?
Wasn't it mod 1 by 2 minus p?
For the first one. Yeah.
For the first one, yes. P, when P is 1 by 2, the error is 0. Yeah, that's right. And beyond that one, I'm not able to decipher anything from this graph. I could see that these 3 straight lines intersecting the P by 10 at different points, and a portion of the line is less than P by 10 and the remaining is more than P by 10. That's all I could see. But how do we message that one? What storyline we are taking that from there?
Yeah, so you saw, right, in the first estimator when we were talking about for the first estimator, like for like more values of p, your error is greater than p by 10, because this
Okay,
was
that's
like
fair.
less than 5 by 11 and then less than 5 by greater than 5 by 9. But if you look over here, like this is slightly lesser than the previous one.
Ma'am, may I ask a question?
Can we leave this error part for some time?
Okay, ma'am.
Yeah, can we move on?
Okay, ma'am.
Still stuck at.
Third graph, yes.
Yeah. So the estimator 3, when we look at, so that estimator was x1 plus x2 plus xn by n, and probability that this error value, that is mod of x1 plus x2 plus xn by n minus of p, this error is greater than p by 10. It is coming to be less than equal to p times 1 minus p upon n p square.
Ma'am, sorry to disturb you. Are you sharing your screen or just your screen?
Is my screen not visible?
It is visible for me though.
Sorry, ma'am, it's not visible to me, ma'am. That's why I'll change my instrument. Thank you.
Okay. Okay, so what we did here is, like, we know this is the error that we had, and we want this error mod of error to be greater than p by 10. So you remember from Chebyshev's inequality, we say that for any random variable x, x minus expected value of x, right, greater than delta, this comes out to be less than equal to variance of x upon delta square. This we know from Chebyshev inequality. So if you notice over here, uh, this p is nothing but expected value of x1 plus xn by n.
Because it's a Bernoulli random variable.
Yes, it's a Bernoulli random variable, right? We are
Yes, ma'am.
talking about Bernoulli random variable.
Yes, ma'am.
Okay.
So variance of x.
That's the reason why it's P there, right?
That's
Am
the
I?
reason it is P there.
And then
Is it? I'm not really sure. I'm asking.
No, that's the reason it is P there. So if this is a random variable, right? X bar minus P. So you would want this, like if you use the Chebyshev's inequality, according to that, it should be less than equal to variance of X bar, right? Variance of X bar upon delta square, that is P square by 100. So here. So, but what is variance of X bar?
P into 1 minus
Sigma
P.
square by n.
P into
P
1
of x
minus
square.
P. It is Bernoulli, na? So P into 1 minus P.
It is P into 1 minus P by
Bernoulli.
N.
N, right?
Yeah.
So it becomes P times 1 minus.
There won't be n, ma'am. Bernoulli, no? It is P into 1 minus P.
It's variance of X bar, right?
Variance of
So
X bar. So
Okay,
if
okay.
you
Yes,
find
yes.
the
Variance
variance of X bar, yeah, right?
Got it, ma'am.
So yeah, so you get 100 times P into 1 minus P divided by NP square. So this is the bound that you get from Chebyshev's inequality. And from there, you can see that as the value of n increases, as n tending to infinity, your probability, the bound on this error, this probability is going to 0. So what it is trying to say is, more the sample sizes, the chances of getting the estimator to be close to the parameter is as less as possible.
Ma'am?
Yeah.
But in lecture, while professor has derived this formula, then he has taken expected value of x as 0.
Expected value of x as 0.
Yes, he has equated it to 0. You can go through the slide. He has equated this to expected value of.
Okay. In the lecture,
expected
what has
value of
been done
error
is
actually.
error.
Yes,
Yeah.
yes.
So
Expected value of error,
there.
he has equated it to 0. Yes.
Okay. So there we have taken the error, and we know error is this x1 plus up to xn by n minus of p, and you are trying to use Chebyshev's inequality, considering this error to be a random variable. You're trying to use a Chebyshev's inequality. So according to that, your probability that mod of error minus the expected value of error greater than delta, where delta here is, p by 10. So greater than delta should be less than equal to variance of error by delta square. So if you find the expected value of error, so this comes out to be p minus p. So this comes out to be 0.
How it is going p minus p, ma'am? Expected value of error?
Error is this, right? So expected value of this is p, and this is p. So p minus p is 0. So these are the, okay, what we just saw, these are things that you should just know how to calculate, like say error. More details you will is not basically a part of this course. So you should know simple things like what the parameter is, what the estimator is,
Okay, we'll
how do you find the error. Yeah.
Once we come to that lecture, then we can discuss. Sorry, I asked it a little bit.
What part?
I think once we go to that part, na, error, bias, and variance, then I can ask this question again. Sorry, I asked it, slightly premature.
No, it's fine.
Ma'am, can you please go back to the previous slide?
So this risk, bias, risk, mean square error, all this
Can I ask a
thing.
question here?
Yeah. Yeah.
I got that part till variance of x bar by p by 100 whole square. After that, ma'am, what happened?
Variance of there.
Yeah. I got till this part.
So what is variance of x bar?
Sigma square by n. Yeah. So sigma square is p into 1 minus p.
So, ma'am, we are getting an upper bound here for the probability of the error to be more than p by 10.
Probability that your error
Is more than p by
by 10 interval is less than p times 1 minus p by 100 times p into 1 minus p divided by np square. So as your number of samples will keep on increasing, probability that your error lies in this p by 10 interval of p is going to be almost 0. Like it will tend to 0.
So then this would make it a better of the best of the three estimators then, as an increase.
Yeah. Yeah. So all this right now you have to know in very deep. So parameter estimation, you have to know a few basic things as part of this course. These have been taught, but like you can just learn what the definition is for now. Yeah. So basically the topics that are really important for this week is how do you design the estimator. So design of estimator is important. And how do you check if your estimator is biased or not? So biasness or unbiasedness. Like these things are more important that you have to take from this week. So first of all, what is the parameter estimation? What is estimator? What is parameter? What are the different ways to design the estimator, and how to check whether your estimator is biased or not. So first we will look at this, like how do you check if your estimator is biased or not. So considering you have a random sample of size n, so this is IID x, okay, and this, let's say this x has the parameter theta. This x has a parameter theta. Then estimator of this theta, that is given by theta hat. We know that this is a function of the sample x1 to xn. And the way we define biasness, so we represent it as theta bias of theta hat of the theta, and this is expected value of theta hat minus theta, right? So since theta hat is a random variable, we can write this as expected value of theta hat minus expected value of theta. So theta is a constant, right? So since theta is a constant, expected value of theta is going to be just theta. So if the bias comes out to be 0, if bias comes out to be 0, we say the estimated theta hat is unbiased. And if the bias is not 0, we call it as the estimator is biased. So we would always want our estimator to be basically unbiased. Okay, so this happens when the expected value of estimator and comes out to be same as the parameter value. So whenever it happens, we will say our estimate, whatever estimator we have found, this estimator is unbiased.
Ma'am?
Yeah.
Now here I can ask that doubt, ma'am. Like as we are discussing that, bias is expected value of error, because error is nothing but theta hat minus theta, right?
Error is, yeah, theta hat minus theta. Yeah.
And bias
so
is
expected value of error. Yeah.
Bias is nothing here. Professor has also said that bias is nothing but expected value of error.
Expected value of error. Yeah, this term is error.
So in case of Chebyshev, that inequality which we are discussing right now, so expected value of error was made to 0. So are we saying that expected value of error will always be 0?
Expected value of error will always be 0. It was not made to be 0. It was coming to be 0, right? Here. Expected value of error was coming to be 0.
Okay, so this is one of the special case where it came, on its own. Getting expected value of error means bias 0. That is our
for
end
some
goal.
For some different estimator, like let's say the second estimator only what we have taken, x1 plus x2 by 2.
Correct.
Right? Like if you try to find the error for this, expected value of this error. Sorry, this was the error, right?
Yes.
If you try to find the expected value of this error, you will get okay.
So
okay, here also it is p minus p by 2. So here also
it
is
will not
0.
be 0. Here it will not be 0.
Here also it is 0, right?
Okay, so that's what is coming. Then can we say that?
But just getting the error to be like expected value of error to be 0. Such estimate like the unbiased is also not something that we look for. I mean, sometimes it can be unbiased, but it may have less variance. So there is something called bias variance trade-off. So there is a trade-off between the bias and the variance.
Why I'm asking this question, ma'am? As per one of the property of arithmetic mean.
Okay.
If if I take the average of differences, then it will always be 0. Like if you have taken 10 values, right? And if you find out the mean of these 10 numbers, and if you translate it like x minus x bar, and if you take mean of these numbers, it will always be 0. So in case of error, while we are doing that calculation, theta hat minus theta, and I am taking the mean of that, and that is my bias. So whether it will always be 0, that is my objective. That is clear to me that bias should be 0. Bias of my estimator should be 0. That is my, that is my desire. But whether it will always be 0 by default, or there will be some cases where bias will not be 0.
There will be cases when the bias is not 0 also. Like,
Sorry.
So, we'll have some example. Like in the case of P1 hat, that is 1 by 2. So in this case, what is bias? Bias of this is just 1 by 2 minus P. Right?
But
so bias.
This is error, ma'am. This is not bias. This is error. 1 by 2 minus P is my error. And if I take the mean of this, that will be my bias.
No, this is my bias only, no. What is bias? Expected value of theta hat. So expected value of 1 by 2 is what? 1 by 2.
No, you just
minus
ma'am, you just
minus P.
You just see the middle part, expected value of theta
No.
hat minus theta, right?
No, what is error? Error is
Theta hat
theta
minus
hat
theta.
minus. Huh.
Yeah, you can write it
See,
down. Theta hat minus theta. That
the
is my error.
estimator is 1/2, right?
Correct. This
And
is
what
my
is bias? Bias is
1/2.
expected value of theta by 2 minus p.
Yes.
So what will come out to be? It is 1/2 minus p bias.
Correct.
So this bias is not 0, right?
Okay, in this case it is
So
not
we are
0.
saying this is an unbiased estimator. Sorry, this is a biased
This is a
estimator.
biased estimator. This is a biased estimator.
Yeah.
If it is 0, then it becomes unbiased estimator.
Yeah, so given any estimator, so whatever we have talked about, you can check whether the estimator is biased or not.
Okay.
So
in case of Chebyshev, whatever we got, that expected value of error becomes
there
0.
it was unbiased. It was an
Okay.
unbiased estimator.
Okay.
You know that this, always remember that this sample mean, so x1 plus x2 plus xn by n, this is always an unbiased estimator.
Okay.
And not just it has like expected value of x bar comes out to be same, even the variance comes out to be the minimum. I think this we had discussed in week 7. So even the variance comes out to be minimum. So that is also one quality that we want our estimator to have. The variance should be minimum.
Got it.
Ma'am, can I ask a question?
Yeah.
Ma'am, here, like, I'm sorry, I didn't get much of the discussion before just happened, but bias is equal to half minus P. And like, if it's a Bernoulli, like P will be half. So like, that will be 0, won't it?
In that case, it is going to be 0.
So if for a Bernoulli,
It depends
half
on
minus P would be an unbiased estimator then?
Sorry, if P?
If like for a Bernoulli P, for Bernoulli half, then this bias would be a good unbiased estimator. This one that you have taken as an example in the discussion that just happened.
But here, not all the samples have been considered, right? I mean, you're saying any sample we take, I will give my estimator to be 1/2.
Yeah, this is the first estimator that we took, right?
Yeah. Like any sample, you are saying, like whatever sample we have observed, we are always saying that we will estimate our parameter using 1/2. So that is not right. I mean, some sample may not give the value, the estimate to be close to 1/2. It may be very far, like the difference can be very far. I mean, the variation can be can be huge between different samples.
I'm sorry, ma'am. I got this reasoning, but looking at that equation, bicycle to half minus P, that does come out to be 0 for P for a Bernoulli distribution. So
Yeah,
despite
only if P is 1/2, you are getting your bias to be 0. But you see, for when you had the estimator to be x1 plus x2 plus xn by n, so see, the P is unknown to us, so we don't know what the value of P going to be. From that example, we just found that the bias is 1/2 minus P. We don't know what P is. Similarly, if we take the estimator to be the sample mean, so there any value, like it is always going to be, biases was coming to be 0. So expected value of this, that was P minus P, was coming to be 0. So here the bias is depending on P, but that P is also unknown to us.
okay, ma'am.
Okay, so in design of estimators, we have 2 different ways to design the estimator. So one is method of moment, and other is maximum likelihood estimator. So these are two different ways to design your estimator. So what we do in method of moment is we calculate different moments of your random variable. So if let's say you have a random variable x and it has some distribution, some fx of x, okay, and this x has parameters, let's say theta 1, theta 2, theta 3, and so on. Let's say your random variable x has these parameters, and if you define different moments of x, right, so it comes out to be one, the first moment is expected value of x, second moment is expected value of x squared, third moment is expected value of x cube. So calculating moments we have learned in week 8, right? So expected value of x, expected value of x squared, expected value of x cube, and so on. We can find different moment of x. So how we have how do we design this estimator as? So we take capital MK, right? So we have different samples. We have a sample x1 to xn, and this is defined as 1 by n sum over xi to the power k, where k is where I is varying from 1 to n. Okay, so this is our estimator. This is our estimator. So once you put different values of k, so let's say I put the value of k to be 1. So putting the value of k equal 1, we get m1 of x1 to xn equal 1 upon n sum over xi, where I is varying from 1 to n. So we know that this is x1 plus x2 plus xn by n.
That is the expected value itself, isn't it?
So this is the first moment, right? So given one sampling instance, given a realization of the random variables, this is your going to be first moment. This is m1. Similarly, you can find the second moment. So x1 to xn, and this is going to be 1 by n sum over xi square. I is varying from 1 to n. And for any, if you have to find kth moment, you will do mk x1 to xn 1 by n sum over xi to the power k, I varying from 1 to n. So similarly, like so what is the
Ma'am, you were
distinction?
telling that one. Ma'am, you were telling that one. Suppose if it is a sixth moment, so when k is 6 and all the other values are 6. But in the last class, when in place of xi,
that was
there was an x square.
that okay. So that we are finding for, like, if you have a random variable x that models the normal, that is x 0 sigma square, mean is 0 and variance is sigma square, then there we are computing the first moment, second moment, third moment. So what is the first moment of x? It came out to be mu. Second moment came out to be
variance,
sigma square, right? But
yeah,
what
variance.
exactly is expected value of x square? It is variance of x minus expected value of x whole square. But here you see, right, here the mean was 0. So that is why this expected, like the second moment of x came out to be just sigma square.
No, that question it was sixth moment, and xi in place of xi it was xi square. So as per the current formula, the sixth term should be the sixth moment. But you were referring that when the coefficient of x power 6 is the sixth moment.
So
Is
there
it
what
correct?
we were doing is we know that mx of lambda was defined as expected value of e to the power lambda x, right? And we had written the expansion of e to the power lambda x and its expected value. Also, we knew that if x is normal mu mean 0 variance sigma square, then mx of lambda is e to the power sigma square lambda square by 2. So we
Right.
wrote this expression and from there we equated we saw compare the coefficient of lambdas.
Yeah, that's exactly that. You just picked reference to the coefficient of lambdas, and we derived the sixth moment. But right now, the formula what you are referring is that should be sixth moment is the sixth term of the series.
So what it is going to be? It is going to be m6 of x1 to xn. It is just 1 by n sum over xi to the power 6.
What is the difference between this one and the exponential series?
What is the difference between this one and the exponential series?
The moment for the exponential series.
From there, what you got? Like this is not even involved. Like exponential term is not even coming. So it comes out to 1 plus lambda x plus lambda square x square by 2 factorial plus lambda cube x cube by 3 factorial and so on. If you take the expected value, it comes out to 1 plus lambda expected value of x plus lambda square by 2 factorial expected value of x square plus lambda cube by 3 factorial expected value of x cube and so on, right?
Okay.
And using this doing this expansion, we got 1 plus sigma square lambda square by 2 plus sigma square lambda square by 2 whole square divided by 2 factorial plus sigma square lambda square by 2 whole cube by 1 by 3 factorial and so on.
Now we can stop that one. So sixth moment is what now?
So these two are equal, right? Basically, we are saying these two are equal. Now let's see. So this gets cancelled out, and we say that we don't have any term which involves lambda in the right hand side. Let's say this is the right hand side. Okay, we don't have any terms that involve lambda in the right hand side. So we can simply say that lambda times ex is 0. Okay, and what is ex? Ex is the first moment of x, that is mean, right? So expected value of x is 0. So that is very evident from here because because the expected value of x is 0, it was already
0.
given.
Yeah, mean is already given as 0. Okay.
So forget about that. So like just compare these two equations. Okay. Now, can you mute? Who is there? Okay. So look at the third term on the left hand side. It has lambda square by 2 factorial, and here also you have a term that involves lambda square, right? So both side you have a term that involves lambda square. So you can compare these two, right? So you can write expected value of x lambda square by 2 divided by 2 factorial is equal to sigma square lambda square by 2. Now from here you can find the second moment, that is expected value of x square, and this is nothing but sigma square because these are getting cancelled, these are getting cancelled, right? So the second moment is sigma square.
Variance.
And if you have, like what we had defined here is, if you have n IID samples, then this is how we define the sample moment to be. Okay. So so this is nothing but 1 by, if you have n IID samples, this is 1 by n sum over xi square I varying from 1 to n. So it's by comparing the left hand side and the right hand side, right? So you can see that lambda cube in the right hand side, we don't have lambda cube. So I can directly say that the third moment here is 0. Yeah. Third moment for what? Third moment for this random variable that follows the normal 0 sigma square. So similarly, you'll have to compare and check, like find all the different moment of the random variable x.
Understood. Thank you, ma'am.
Ma'am?
Yeah.
Just a very small doubt, ma'am. Here we started with a normal distribution which is having 0 mean, right?
0 mean. Yeah.
Yes. Mean is 0, right?
Mean is 0, variance is sigma square.
Correct.
Yeah.
So mean is 0. That is the reason why my second moment is equal to sigma square. If mean would not have been 0, then second moment will be sigma square plus mu square, right?
Yes, sigma square plus mu square.
Yes, this was my doubt. Means second moment is not always equal to variance. We can't say.
Yeah, you cannot say that second moment is equal to variance. It came out to be variance here because the mean was given to be 0.
Correct. Thank you, ma'am. Thank you.
Would we expand that series, madam, if we really have both? I mean, if mean is not equal to 0, maybe just for a term.
But do we know? We don't know what the MGF of normal mu sigma square. We knew the MGF of normal 0 sigma square. We can find it, but we'll have to calculate.
Okay.
I don't recollect it at this point of time. In fact, Srikant sir had derived that. In one of the live session, he had derived that. I am just forgetting that.
Yeah, derived?
Yes,
Yeah,
sir,
you
he had
can
derived. He has
check.
written, he has not derived, he had written directly. He had derived this e to the power sigma square lambda square by 2. And the second one he had directly written. I am just forgetting it. Sir. No problem. I got my doubt clarified, ma'am. Thank you. We can move ahead, ma'am.
Yeah. So what happens is, like, generally we see that these moments are mostly many a times expressed as a function of these parameters. So if you come across, like, if you have to if you know the distribution, how do you design the estimator of the parameter using method of moment? So that we'll have to learn here. So okay. So given a distribution, how do you design the estimator using method of moment? So let's start from very simple example, that is of Bernoulli. So let's say you have x1 to xn, that is Bernoulli P. Okay. Now we know that the estimator of this P is P hat. Okay. So this P hat can you mute? Okay, so here I will just show how do you like find the method of moment estimator if you have just one parameter. So in case of one parameter, in cases of one parameter, what you do is you equate expected value of x, okay, expected value of x to be m1, and whatever m1 you get, this comes out to be your this is your method of moment estimator. So for example, in case of Bernoulli P, you know the parameter is P, and what is the expected value? Expected value of this P is expected value of this random variable x is P. Now we will equate this expected value of x to be equal to m1. So what is this? This is P equal m1. And what exactly is p1? What exactly is m1? M1 is nothing but x1 plus x2 plus up to xn by n. So this small m1 is just for one realization of the random variable x1 to xn. So this m1 is for one sample. But if we have to say for in general, we'll say this m1, that is nothing but this will give our estimated p hat, and this is capital X1 plus capital X2 plus up to capital Xn by n. So this is the method of moment estimator for the Bernoulli P. Similarly, we have, let's say, the samples coming from the Poisson lambda distribution. So what is the first thing that we will do? We know that expected value of x is lambda, and we will equate this expected value to be equal to m1. So this is nothing but m1, and we know m1 equal x1 plus x2 plus xn by n. So let's say this we define the estimator of lambda to be lambda hat. We can also write mme here for the convenience that this is designed using the method of moment, and this is coming out to be capital M1, and this is x1 plus x2 plus xn by n. But if you have, let's say, exponential distribution, exponential lambda, so it will vary a little. So in case of exponential, we know that expected value comes out to be 1 by lambda. So 1 by lambda equal m1, and lambda hat mme for exponential distribution will come out to be n upon x1 plus x2 plus xn. So this is for exponential distribution. But so these were the example when you had one parameter. So if you have one parameter, this is how you will find the estimator using method of moment. Like whatever expected value of the distribution is, you equate this distribution, you equate this expected value, like distribution expected value, to be equal to the first moment, because we know the first moment gives the expected value. So equate this distribution mean to the sample mean, and from there you find the estimator. But in case you have two parameters, like as in case of the normal distribution, so we know that in normal distribution we have two parameters, that is mu and sigma square. So what we do in this case is, so the first is same as what we have done in the previous one. So we first write expected value of x, so distribution mean equals to mu, and we equate this to m1. So once you equate this to m1, we know that this method of moment estimator for mean comes out to be x1 plus x2 plus xn by n. This was the same as the previous one. Now if we have to find, if we have more than one parameter, we go to the second moment. So if we had just one parameter, we equated just the first moment, right? We just found one moment. But if we have, let's say, two parameters, we'll go for the second moment. So the second moment, we know expected value of x square. Expected value of x square is what? This is variance of x plus expected value of x whole square. And what is variance of x? It is sigma square. It is given to be sigma square, and expected value of x is mu square. So sigma square plus mu square. Now we'll equate this expected value of x square to be equal to m2. And what exactly is m2? M2 is 1 by n sum over xi square, I varying from 1 to n. And this will come out to be 1 by n x1 square plus x2 square plus up to xn square. And we will have to equate this expected value of x square that came out to for like the distribution of x, it was sigma square plus mu square. So we'll equate this to sigma square plus mu square. And from here, sigma square, we'll say this sigma square hat or MME will come out to be sum over xi square divided by n minus of mu square. So this mu, you will have to use what so this mu is also should also be an estimator. Okay, so what was the estimate method of moment estimator of mu? And this was sum over xi upon n. So this is the estimator for sigma square. So this was in case you had two parameters for a distribution. So what you do first is you find the first moment of the distribution mean. So the distribution mean is mu, right? So you equate the distribution mean. First step is equate distribution mean, that is expected value of x, to be equal to this first moment of the sample. The first moment. Okay. Then from there you will get one parameter, like the estimate for one parameter. Then for the second parameter, you equate the second moment of the distribution, second moment of x, you can say second moment of x, to be m2. Here it is instead of distribution mean, this just write it, equate first moment to be equal to m1, equate second moment of x to be equal to m2, and then find the second parameter. So this is the way we find the estimator for different distribution, different parameters. Any doubt in how we find the method of moment estimator? Any doubt in how to find the method of moment estimator?
No, ma'am.
Okay, so
Ma'am, can you go 2 slides back with one parameter distribution?
yeah.
Yeah, here. So you said Bernoulli and Poisson, and how do we handle an exponential distribution? And what is it? What is the relation between Poisson and exponential?
So for Poisson, what did you get? You get the lambda hat to be x1 plus x2 plus xn by n. But for exponential, you got the reciprocal of sample mean.
Oh, okay. It's a reciprocal of the Poisson.
Yeah.
That means x1 plus x2 xn divided by n.
So we can stop at method of moment for today. Maximum likelihood we can look on Sunday session.
Ma'am?
Okay,
Yeah.
ma'am.
Ma'am?
Okay, ma'am.
Okay, yeah. Tell me.
When we started talking about this estimator evaluation calculation with the help of methods of movement, I have some doubt in risk and variance. Risk is clear. In variance, I have a specific doubt. Let me ask that doubt.
Okay.
Variance of error and variance of estimator. Professor has derived that both means same. So this is not clear
Variance
to
of
me. Variance of error plus variance of estimator means theta hat are same. This
variance
derivation is
of
not clear to me, ma'am.
error.
And variance of estimator means
Okay.
variance of theta hat you can say.
Okay, you're asking how these are same.
Yes,
Okay.
yes. Professor had
So
done that
what
derivation,
is
but I
what
am
is
not.
error? What is error? Error is
Theta hat minus
theta hat
theta.
minus theta. You know
Yes.
that theta hat is a random variable, but
Yes,
theta
yes,
is
yes.
a constant.
Yes.
So this is just going to be variation of theta hat. Sorry, variance of theta hat. Because variance of a constant is going to be 0, no?
Variance of a constant is going to be 0.
Theta
Okay.
is what? Theta is a
So,
constant.
using this logic, we are saying that it is equal to variance of estimator, right?
Yes, yes, yes.
Okay, okay. I thought that there must be some mathematical derivation.
No,
No,
no, no.
going by this logic, it's clear, ma'am.
Yeah, because theta is a constant. Theta is a parameter. So
Yes, yes, I
variance
know
of,
theta is a
yeah.
parameter that I know. Theta is a parameter. But ma'am, does it mean that these two are independent?
These two are independent?
Means theta hat and theta are independent. Does it mean, because we know that variance of
Theta hat,
no, we
theta
know that
hat is a random variable.
yes, and theta is
And
constant,
theta
right?
is a constant.
Theta is a constant. Okay. Okay.
Theta hat is an
Yes,
estimate,
yes,
is it?
yes, got it right. It's a parameter. Theta is a parameter.
Yeah.
Okay. Ma'am, if the time permits, ma'am, I have a doubt from graded assignment of last week. It will not take more than
Last week. Okay.
yeah, means week 8. Question number 5 and
Okay.
6, ma'am. Even just a small disclosure, the same questions were explained in live with live
Solve with us session.
solve with us session during the live session. But I had not understood, so I didn't attempt these questions in graded assignment also, ma'am. By copying that, I could have done that, but I had not understood, ma'am. So if your time permits, we will not take more than 5 minutes. Question of 5 and 6, that is, ma'am, like one is
Okay, I
WLLN method.
remember it is
I am saying
probability mod of x by n minus 2.
Yes.
What was that? X
Okay.
by n minus 1?
Just a second, ma'am.
Greater than 0.02 something.
Just a second, ma'am. Yes, ma'am. 5 is x by 2n minus 1.
X by 2n minus 1.
Mod greater than 0.01.
Greater than 0.01.
And then the probability of the entire expression should be less than 0.01. So I repeat, probability of bracket mod of x by 2n minus 1 greater than 0.01 should be less than 0.01. So using the weak law of large number, we have to find the number of sample.
And you know that x is gamma random variable, right?
Yes, x is gamma random variable with parameter alpha beta, alpha beta, and the sum of n independent gamma will be gamma n alpha by beta, n alpha comma beta.
Yes.
It is given
So-
alpha equal to 2n, right?
I don't know what the question is.
Yes, ma'am.
Yeah, alpha is equal to n.
Okay, so alpha equal
Beta is
2n comma beta.
Ma'am, I had
Beta is
What you are
one.
saying?
Ma'am, I had given the disclosure earlier itself. The same problem was discussed in solve with us, but I had not understood. That is the reason I'm asking second time.
Okay.
If I remember it
So
right, it is 2n comma 1, madam.
2n comma 1. Okay.
Yeah.
Yeah, it makes more sense. Let me have a look for the question. That will be better.
The same problem has been asked to solve using weak law of large number and then CLT.
Yeah, I know the question. I know.
Ma'am, may I say something?
So x by 2n minus 1 greater than 0.01 less than equal to 0.01. So x is a random variable with parameter alpha 2n beta 1. Okay. Okay, so this was the question. Now you can, what you can do is, so if you have to use weak law of large number, right?
And then
To
CLT,
find the
yes.
value of n.
Yes.
So weak law of large number, what does it say? It says that probability mod of x bar minus expected value of x bar, right? Greater than some delta is less than equal to variance of x bar divided by delta square. This is weak law of large number, we know. Now,
And ma'am, this is as per Chebyshev inequality also, right?
Yeah.
Okay. Okay.
So we can write this x to be, x1 plus x2 plus xn, sorry, x2n divided by 2n minus of 1. Okay. We can write this, right?
Yes. Yes.
So what we're saying is each of the xi here will become 1 comma 1 comma 1 comma 1, right? Using the property of gamma distribution. So if you have x1, x2 up to xn gamma alpha beta, then x1 plus x2 plus up to xn becomes gamma n alpha comma beta. So what I'm doing here is I'm just writing x bar x as x1 plus x2 plus x2n divided by 2n. Okay, so we know that x1 plus x2 plus x2n is going to be each of these xi's are going to be gamma 1 comma 1, right? This is clear. Each of the xi is gamma 1 comma 1. Now, okay, now this is what, this is basically sample mean, right? So I can write this as mod of x bar minus, so what is going to be the expected value of x bar here? Expected value of x bar, it is going to be 1.
No.
It is going to be 1 here, right?
As per formula, it is alpha by beta, no?
Sorry, alpha by beta. So what is alpha by beta? Alpha by beta is
Yes.
1 by 1.
Yes.
So this is
Yes.
1, right? So this is what we have. So this I have written as x bar, and this is nothing but expected value of x bar to be equal to 1, right? So this is done. Now we are saying greater than 0.01. This should be less than equal to variance of x bar divided by 0.01 whole square. Now what is variance of x bar?
Alpha by beta
Variance
square.
of variance of x bar means variance of x1 plus x2 plus x2n divided by 2n. And this is going to be 1 by 4n square 2n times variance of each of the xi. And variance of each of these xi is going to be alpha by beta square. So basically 1. So this is going to be 1. And variance of x bar become 1 upon 2n. So this I can write it as 1 upon 2n into 0.01 square, and this is going to be less than 0.01, and from there we can just find the value of n.
Okay.
Right. So similarly, you can do for CLT. The same approach you can use for CLT. So why this question has been asked using both the method?
Can we take a fresh
So why?
Can we take a fresh case for CLT?
Okay, so if you look at CLT, so it is probability that mod of x upon 2n minus 1 greater than 0.02 is less than, 0.01 is less than equal to 0.01. Now, if you have to use CLT, what does the CLT say? It says your x bar minus mu, basically expected x bar minus
n mu.
let's not write this. Yeah, let's write mu only. So x bar minus mu divided by sigma upon root n. This is normal 0, 1. And what is x bar? X bar is x1 plus x2 plus xn by n, and expected value of each of these xi's are mu, and variance of each of these xi's are sigma square, and we are saying x1 to xn are IID x. Now, if you have to use CLT, you will have to make this into, so probability that x1 plus x2 plus up to x2n divided by 2n minus of 1 greater than 0.01. So, okay, so this is nothing but your x bar, right? So probability that mod of x bar minus, what is 1? 1 is nothing but expected value of x bar, that is mu. So x bar minus 1 greater than 0.01, right? Now we will have to divide this by sigma upon root n. So what is sigma of here?
Alpha by beta square.
Alpha by beta square. So basically 1. So 1 divided by root n. So 1 divided by root n, and here also we can just multiply root n, right? So you will see that this is nothing but your z. So probability that mod of z greater than 0.01 under root n is less than 0.01. So can you solve it after this?
Yes, ma'am.
Yeah.
Yes.
So why this question had been asked for both weak law of large number and CLT? You will see that you will need a large value of n to get this bound. You will need a large value of n to get this bound when you do using weak law of large number. Yes. But in case of CLT, even with a small value of comparatively smaller value of n, smaller sample size, you can get the same bound. So that is why CLT gives you a better, like stronger bound. Like good approximation. CLT better gives a good approximation.
Yes.
Madam, I have a question here.
Yeah, for this one.
No, you are coming on Sunday.
Shrikant will be taking the session on Sunday.
Okay, so just pass on up to what portion we have completed so that we can.
Yes, yeah.
Madam, I have a question. The same gamma distribution.
CLT has a relatively smaller value. Is that ma'am?
Let me complete, buddy.
No. It's a continuation of this one. That's what I jumped.
Yeah,
she is wrapping up this one. And, the CLT is relatively smaller than the. Now comparing the weak law of large number and CLT, the n value is relatively small.
Yeah.
N value is relatively smaller.
Yeah. You need smaller sample size to get the bound.
Okay.
Yeah.
Thank you, ma'am.
Yeah, who was asking?
Yeah,
Ravi, right?
my question is like normally we are taking alpha and beta values as 1. Is it necessary that alpha and beta values be 1? Can they not be in this case, like if it is n alpha and beta, can I not actually take it as 2 as alpha? I mean, is it really necessary that I have to get to alpha?
If you
How
are
should I
okay,
interpret
so
that?
what we are writing as, we are writing x to be x1 plus x2 plus xn, right?
Yeah.
And this x was gamma 2n comma 1.
Correct.
Right? Using the property of gamma distribution, we know that if you have x1 to xn, IID gamma alpha comma beta, and so if we have to take the sum of these random variable, it becomes gamma n alpha beta.
Correct.
So looking at this, we have alpha to be 2n, right? So if you take individual x1 to xn, it should come out like this is 2n, then each of these xi should be gamma 1 comma 1, right?
Yeah.
By comparison, you can say that, right?
Yeah. Yes.
Yeah. So what was your
What I
doubt?
was asking is, if I take it only till xn, then can I assume? Then can I assume something else is what I was just thinking, and I was just.
If you take it just
I'm having 2 n samples.
In
Okay.
that case, alpha will be 2, I think.
Alpha will be 2.
Yes, in that case, alpha will be 2.
And can I not use that to solve the problem is what I was thinking.
That's a valid question.
You are saying if you
let me
x to be
if I go only algebraically, x by 2n minus 1 mod is greater than 0.01. That is all it is. So I can actually put it as x minus 2n. I will not go into an expansion of IIDs. I'll just keep it as x minus 2n by 2n mod, enter mod, is greater than or equal to 0.01. I will move the 2 to the other side and I will say x minus 2n by n is greater than or equal to 0.02.
You can do that. So you will have x minus 2n divided by 2n greater than 0.01. So if you take 2n to the other side,
then
so it becomes x by 2n divided by n greater than 0.02. Yeah.
This also resembles weak law of large numbers.
Yeah, I mean, it is not nothing about weak law of large number. You're just doing
Yeah, because I went by this approach. I was not sure if when you started explaining it the other way, I was wondering if what I did was absolutely wrong or something. Yeah.
No, so x minus 2n, right? You have x minus 2n here.
Yeah.
Now you have to solve it using weak law of large number.
Yeah.
So
x minus mu is greater than delta.
You can do x by n minus 2. You can write this, right?
Yeah, which
now
is still x bar.
2, won't it?
Sorry?
Yeah.
Now won't the mu be 2? Previously, when we took 2n, mu was 1. Now the mu will be 2, isn't it?
Mu is 2.
So if you write now x to be x1 plus x2 plus, it is again x2n only.
No, ma'am. Here it will be till xn. No.
Sorry?
No, it will still come as 2n because it is x by n minus 2. See, if I actually go for the bracket, if you see what is that is written there in the mod in the center of the page, where ma'am has written x minus 2n by n, it is still 2n. Okay, it's still 2n. Okay. Only thing is within the probability now this value should be greater than 0.02, but by weak law of large numbers that constant will still be less than 0.01. That also gives the same answer.
You can try. I don't know if you can put this into like this form. If you can put this into this form, you can just solve it.
Actually, I tried that, and that's how I ended up with the numbers. And whatever I picked for both 5 and 6, I use the same procedure. Only I played with the whatever with the function that is there within the probability, and left out the less than or equal to 0.01. I didn't actually change anything on that one. I got the answers. I just picked them. I hope I got them right.
Your answer is right, no?
Yeah, it's
Come out, no?
It's sorry. Yeah, answer is right.
Okay.
The answer is right. So now I'm wondering if it was a fluke or if it was
No, already the result.
okay to do that.
Yeah.
Okay, so what? Okay, can you tell me what you did? You did probability mod of x. Yeah, okay, so we reached at x minus 2n by
n is greater than
0.02 is less than equal to 0.01.
Right.
And what we want is probability that mod of x bar minus expected value of x bar greater than some delta.
Yeah.
Okay.
In fact, I did not actually. Sorry. One small correction. I did not actually commonize between x by 2n and this. I went directly for because it is mod. It is going to come twice. So 2 minus.
Why will it come to be twice?
It's a positive value, isn't it? Mod when I actually say.
Okay. Oh, what you did? You did.
I'm going only for one side of the function, but.
Okay. So you're saying x minus 2n by n greater than 0.02.
0.02, yeah.
Okay.
And now my delta is sigma square is 2.
Sigma square is.
Because it's alpha by beta square. Alpha, I'm taking it as 2 now. It's not 1.
Hello, can I say something, please? This
Yes,
should be the variance of the sample mean, right? So sigma square divided by 2n if you are taking up summation till 2n, and then sigma square by n if you are taking summation till n. So if your sigma square is 1 there, then you should get 2n in the denominator, and I think that's
sigma square is 2 is what I'm saying, because it's alpha by beta.
Then you divide it by n, right?
I'm dividing it by n, yes. Sigma square by n delta square is what I'm going for. Sigma square is alpha by beta square. That is 2 because I'm taking a beta of 2 now.
Yeah, and your delta is 0.02.
0.02.
Right?
Yes, 0.02 square. So
okay,
n is coming out as greater than 500,000.
Okay, can you do one thing? I don't know how did you solve this. Can you post whatever way you have solved it? Can you post it on Discord?
Sure.
And tag
Sure.
me. I will check it there. Yeah?
Yes, ma'am. Yes, thank you.
Yeah.
Should I tag you or?
Yeah, you can tag me.
Thank you.
Yeah.
Ma'am?
Yeah.
As the procedure for Chebyshev and weak law of large number, that expression for inequality is same. So are we saying that both of them are same, like Chebyshev inequality and weak law of large number?
Chebyshev's inequality, we're looking for just one random variable, but weak law of large number is for a IID sample.
Okay.
Yeah.
Okay. That is more generic.
Can you repeat that once again, madam, please?
So Chebyshev's inequality is we are writing it for just one random variable, but when we are talking about weak law of large number, we are actually doing it for a random sample. We're checking it for a sample, but there it is just one random variable.
So weak law.
There is a lot of similarity in all the three.
Sorry?
Weak law of large number is a generic case and Chebyshev is a special case of weak law of large number. Can we say like this now?
Weak law of large number is a special case of Chebyshev's inequality.
Chebyshev is a special case of weak law of large number because weak law of large number is dealing with multiple samples, na?
No, like you are Chebyshev's inequality is the like
That is for only one
thing.
value.
You are extending that Chebyshev's inequality to n random variable.
Yes, that's what I'm saying. Na? So Chebyshev is a special case of WLLN. Can we say that?
Special
I don't
case
think
of,
that's what was said in the episode.
it's
Yes,
opposite.
I'm just asking that can we say like this?
It's opposite actually.
Okay. Okay, ma'am. Thank you. Thank you.
Yeah.
So
Yeah.
these
Yeah,
three are
that's all. So
related.
we'll discuss
Weak
it
law,
later.
log number, and CLT are related.
Now we are towards the end of our course, ma'am. Week 10 content has
So
been released
weak law
today.
of weak law of large number and CLT is almost the same thing.
It's fine. It's already 10:25. I just said that now we are towards the end of our course. Week 10 content
Yeah.
has been released today.
Yeah.
No,
So
week 10 is late. You don't need to bother about it. That's somewhere around 20th.
Okay, thank you.
Thank you very much,
yeah.
ma'am.
Yeah.
Thank
Thank
you,
you
ma'am.
also. Yeah. Maximum likely estimator we'll discuss on Sunday.
Thank you. Good night.
Thank you. Good night.
Thank you.